essentially what happened before the Big Bang. Right? You have to be careful with the language. So if you define the Big Bang really carefully as the time when the universe was very hot and very dense, how the universe got into that state is that there was a time before that.
The Big Bang Theory, the dominant model for explaining the birth of our universe, describes a singular point roughly 13.8 billion years ago, when space, time, and matter as we know them came into being. From this moment of unimaginable density and heat, the universe expanded, giving rise to the galaxies, stars, planets, and all matter that we observe today. But despite the widespread acceptance of the Big Bang Theory, it leaves open one of the most intriguing and terrifying questions. What, if anything, existed before the Big Bang? Traditionally, asking about what existed before the Big Bang is paradoxical because, in the Standard Model, time itself began with the Big Bang. If time didn't exist beforehand, then there was no before. But now, many scientists, including renowned physicist Brian Cox, have started exploring what might lie beyond this boundary, using emerging theories to peer back into a realm that defies conventional understanding. The answers are speculative but tantalizing, hinting at a universe that may be far stranger and more complex than we can imagine.
So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again.
After all, what exactly happened before the Big Bang? Could the universe start with a bounce or something else entirely? Join us in today's episode as we dig deep into one of the thorniest in physics. To understand why the idea of a before the Big Bang is so tantalizing, it's essential to grasp how the Big Bang model explains the origin of the universe. The idea that the universe had a beginning, or a day without a yesterday, as it was originally known, goes all the way back to Georges Lemaitre in 1927. Although it's still a defensible position to state that the universe likely had a beginning, that stage of our cosmic history has very little to do with the hot Big Bang that describes our early universe. Although many laypersons and even a minority of professionals still cling to the idea that the Big Bang means the very beginning of it all, that definition is out of date. The Big Bang now is not the birth of time and space. We know that today, in 2023. In fact, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures. There's a cutoff. Instead, our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. There were no particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time, by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new small-scale fluctuations are created atop them. This superposition of fluctuations, of small scales, atop intermediate scales, atop large scales, atop superhorizon scales, is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on, but inflation will come to an end randomly, and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang, before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately a trillion to the power of -33 seconds or so. A brief amount of time, but nonetheless one that is not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise, from just a few degrees above absolute zero to perhaps intentosis Kelvin or so, over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All quanta will behave as radiation with so much kinetic energy inherent to them, regardless of whether the particles are massless or massive. It doesn't matter under these conditions. This conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'll witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats and the hot Big Bang starts. More distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate there drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, that distance doubles yet again, and again, and again. The process is relentless. But once the Big Bang begins, all of that changes, as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation, and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region within space-time, dominating its volume. These regions where hot Big Bangs occur will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes where separate hot Big Bangs occur will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and the only departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. The typical difference might only be at the 3% level, but that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later, after they've undergone countless interactions. Even at that, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations that are imprinted on the first picture of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are a lot of inconsistencies between the cosmic microwave background and our current model of cosmology. We're missing something. These can be summarized in 4 anomalies. First, on very large scales, the universe isn't acting like we think it should. Second, light from the cosmic microwave background will be lensed by matter in between us and the cosmic microwave background. This means that matter acts like a giant lens, bending and changing the amplitude of the light behind it. The amount that this happens is not consistent with our current model of the universe. This is such a significant problem, it has sometimes been called a crisis for cosmology. Third, the 2 hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make a lot of sense since we believe that the universe should have started out uniform, on average. And last, the value of the Hubble constant, which describes how fast the universe is expanding, is different whether we measure it from the cosmic microwave background or from more nearby Cepheid stars. Taken together, these anomalies mean we're missing something fundamental in our understanding of the universe. Brian Cox delves into the heart of the issue. The idea that something existed before the Big Bang challenges traditional scientific assumptions, particularly the idea that time itself began with the Big Bang. In the standard cosmological model, time, like space and matter, came into existence at the moment of the Big Bang. As such, asking what happened before the Big Bang is somewhat paradoxical in this framework, akin to asking what is north of the North Pole. However, emerging theories in physics and cosmology suggest that time and space may not be as simple as they appear. Concepts like quantum gravity, string theory, and the multiverse offer potential ways to break down the boundary set by the Big Bang. These theories propose that our universe may be one of many, each with its own space-time framework and physical laws. Brian Cox has referenced these theories, suggesting that the Big Bang may not be the beginning of everything, but merely the start of our particular universe. One hypothesis gaining attention is the idea that our universe is part of a multiverse, a collection of universes that exist simultaneously. In this model, each universe within the multiverse may follow its own distinct physical laws, exist in separate dimensions, and have its own timeline. The Big Bang, in this context, may represent the birth of our universe within the multiverse, rather than the birth of all existence. If the multiverse concept holds, then the conditions before the Big Bang could be vastly different from anything we can observe or understand within our own universe. This suggests the possibility that what existed before the Big Bang was an entirely different kind of universe or reality that operated under laws alien to our own. Another perspective Cox has touched on is rooted in the concept of cyclic or oscillating universes. According to this model, the universe goes through infinite cycles of expansion and contraction, with each cycle ending in a big crunch that leads to a subsequent Big Bang. In this view, our universe's Big Bang was simply the latest in a long series of cosmic rebirths. This cyclical model offers a fascinating, if somewhat eerie, view of the cosmos, a universe without a true beginning or end, eternally looping through life, death, and rebirth. Such a model also implies that each cycle may differ in structure, composition, and physical laws, suggesting that the universe that existed before our Big Bang could have been vastly different from our own. Quantum mechanics, too, has intriguing implications for understanding pre-Big Bang conditions. In the quantum world, particles exist in states of probability rather than definite locations. Some physicists suggest that before the Big Bang, the universe was a quantum vacuum, a state of infinite potential where particles flicker in and out of existence. In this state, rather than the universe existing as we know it, there was only a sea of quantum fluctuations, essentially a void of possibilities that, for reasons not yet fully understood, eventually led to the Big Bang. This quantum vacuum could have harbored unknown energies or forces, creating a precarious balance that eventually gave way to the explosive birth of our universe. Brian Cox has also discussed the idea that time itself may not be a linear progression from the Big Bang to the present. Some theories propose that time could behave differently on a cosmic scale, with the Big Bang representing not a single isolated point, but part of a larger, interconnected timeline. This suggests that time may flow in both directions, or that there are multiple pasts and futures branching off from the Big Bang. If true, then what we perceive as the beginning of time might simply be a single point on an infinite web of timelines and possibilities. In this view, what existed before the Big Bang could be one of many possible pasts, some of which might be incomprehensibly different from our universe. Another chilling theory Cox has discussed is rooted in the notion of higher dimensions. Our universe exists in 4 dimensions, 3 spatial dimensions, and 1 of time. But theories like string theory and M theory propose that additional dimensions may exist beyond those we can perceive. According to this idea, the Big Bang may have been a collision between higher dimensional brains or objects that exist in a larger dimensional framework. The energy released in this collision could have triggered the formation of our universe, creating the space and time we experience. If this is the case, then what existed before the Big Bang may have been an unobservable realm of higher dimensional objects and forces. The possibility of higher dimensions brings an eerie aspect to the notion of pre-Big Bang existence. These higher dimensional realms could harbor entities or energies that defy human understanding, existing outside of space and time as we know them. This has led some theorists to speculate that the universe before the Big Bang could have contained unknown, perhaps even malevolent forces. While this idea strays into the realm of science fiction, it highlights the limits of human comprehension and suggests that the ultimate nature of reality may be beyond our ability to fully grasp. One of the most profound ideas that Cox has explored is the notion of the anthropic principle, which states that the universe's properties are fine-tuned for the existence of life. Some scientists argue that this fine-tuning suggests a deeper level of design or intention, implying that the universe may have been created with life in mind. In this context, the conditions before the Big Bang could have been meticulously arranged to ensure that a universe capable of supporting life would emerge. This raises profound questions about the nature of existence, consciousness, and the purpose of life. If the universe is designed with life in mind, then whatever existed before the Big Bang may have played a crucial role in setting the stage for our existence, suggesting a hidden complexity to the cosmos. Another theory that provides a chilling perspective on the pre-Big Bang universe may lie in loop quantum cosmology. Loop quantum cosmology arises from loop quantum gravity. In loop quantum gravity, gravity itself is made of particles called quanta. These quanta come together to form the fabric of space and time. In this model of the universe, there is a smallest size of space itself, the Planck scale, or 10 to the power of -35 meters. Nothing, not even space itself, can be smaller than this. This means that the Big Bang couldn't exist in a universe with loop quantum cosmology. The universe could never get down to an infinitely small, infinitely dense point. Close to the Big Bang, when the universe was very small, really weird things happen mathematically. Infinities start to arise and threaten to tear the fabric of space-time itself. It's at these locations where loop quantum gravity can come in to provide corrections to the physics we already know. As Dr. Abhay Ashtekar at Penn State University, who led a study showing that the universe started in a bounce rather than a bang, said, "At such places, one has to use quantum geometry underlying loop quantum gravity. The quantum-corrected equations predict that there is an effective repulsive force. This means in these regions when the universe is very small, the repulsion would result in a bounce. If our universe originated in a bounce, that means there was another universe before us. That universe went through its life, perhaps expanding and eventually contracting once again. As all of the matter and space-time of this universe came together, it ended in a spectacular fireball. Then, in a giant bounce, our universe was born, like a phoenix rising from the ashes of the old universe. This isn't entirely a new idea. Physicists have tossed around the idea of the Big Bounce for several decades. Even farther back, cyclic time is present in Hindu cosmology. If loop quantum cosmology is the correct model of the universe, in its infancy, the universe would have had very high curvature. To visualize this, think of a globe has positive curvature, a sheet of paper has flat curvature, and a saddle has negative curvature. If the universe was strongly curved when it was young, evidence of this would show up in the cosmic microwave background. When you look at the cosmic microwave background, you realize that it is not uniform. It's close, but there are small differences in temperature from one point in the sky to another. If you plot these temperature differences as a function of scale, you get one of the most powerful tools of cosmology, the angular power spectrum. Evidence of the curvature of the early universe would show up in the angular power spectrum of the cosmic microwave background. Some of these effects would show up at extremely large scales, larger than the size of the universe. This is a problem, obviously. We won't be able to observe it. However, luckily for us, these large scales interact with smaller scales, providing us with indirect evidence of this early phase of the universe. One of the effects of these interactions is to create the hemispherical anisotropy, says Ashtekar. In our current understanding of the universe, the probability that the two hemispheres of the sky would be different is very small. But with loop quantum cosmology corrections, the probability is enhanced and the observed anisotropy is no longer anomalous. That means that loop quantum cosmology would provide an explanation for anomaly number 3, why the hemispheres in the sky have different average temperatures. In addition, using the model of the universe that loop quantum cosmology provides solves the first 2 anomalies that we have seen in the cosmic microwave background: strange behavior at large scales and lensing. According to Dr. V. Srinath of the National Institute of Technology, Karnataka, this possibility that cosmic microwave background anomalies are not just statistical flukes, but rather effects due to quantum gravity happening very early in the universe is very exciting. But how sure are we that the universe originated in a big bounce? Except that, with all major claims, extraordinary evidence is needed. The idea that the universe originated in the Big Bounce has been suggested several times. We'll have to see if this one sticks. Another problem: our observations are limited, and it may just be that we are observing a part of the universe that is unusual. That's a problem called cosmic variance. As Dr. Donghui Zhang, a co-author of the paper and professor at Penn State University, said, "It is hard to confirm with 100% confidence because of the cosmic variance. But what is intriguing is that including this new possibilities can resolve 2 issues at the same time: the large-scale power suppression and small-scale lensing amplitude." Ruling out signs of an loop quantum cosmology-driven cosmic bounce in Planck data means the cosmic microwave background anomalies remain unexplained. But an even larger cosmic issue lingers. Did the universe have a beginning at all? As far as advocates of the Big Bang are concerned, it did. But that leaves us with the inscrutable singularity that started everything off. Alternatively, according to theories of so-called cyclic cosmologies, the universe is immortal and is going through endless bounces. Although a bouncing universe may experience 1 or more cycles, a truly cyclic universe has no beginning and no end. It consists of a series of bounces that go back for an infinite number of cycles and will continue for an infinite number more. And because such a universe doesn't have a beginning, there's no Big Bang and no singularity. But physicist William Kinney of the University at Buffalo points out that there is a critical flaw lurks in the idea of an eternally cycling universe. That flaw is entropy, which builds up as a universe bounces. Often thought of as the amount of disorder in a system, entropy is related to the system's amount of useful energy. The higher the entropy, the less energy available. If the universe increases in entropy and disorder with each bounce, the amount of usable energy available decreases each time. In that case, the cosmos would have had larger amounts of useful energy in earlier epochs. If you extrapolate back far enough, that implies a Big Bang, like beginning with an infinitely small amount of entropy, even for a universe that subsequently goes through cyclic bounces. New cyclic models get around the problem by requiring that the universe expands by a lot with each cycle. The expansion allows the universe to smooth out, dissipating the entropy before collapsing again. Although this explanation solves the entropy problem, Kinney and his University at Buffalo co-author Nina Stein calculated in their recent paper that the solution itself ensures that the universe is not immortal. As Kinney says, "I feel like we've demonstrated something fundamental about the universe, which is that it probably had a beginning. That implies a Big Bang occurred at some point, even if that event happened many bouncing universes ago, which in turn suggests that it took a singularity to get everything going in the first place." Kinney's paper is the latest in the debate over cyclic universes, but proponents of a universe without beginning or end have yet to respond in the scientific literature. 2 leading proponents of a cyclic universe, astrophysicists Paul Steinhardt of Princeton University and Anna Aegis of New York University, declined to comment for this article. If the history of the debate is any indication, though, we may soon hear of a workaround to counter Kinney's analysis. Some physicists say the Planck data only rule out a bounce under a loop quantum cosmology model that can explain away the cosmic microwave background anomalies through the bispectrum, not other loop quantum cosmology bounce models that address anomalies using different mechanisms. Cosmologist Nelson Pinto Neto of the Brazilian Center for Physics Research, who has studied bouncing and other cyclic models, agrees that loop quantum cosmology bounces that account for the cosmic microwave background anomalies are likely off the table now. But he's more sanguine on the question of a cyclic universe. According to Nelson, existence is a fact. We are all here and now. Non-existence is an abstraction of the human mind. This is the reason he thinks that a cyclic universe, which has always existed, is simpler than one that has been created. However, as a scientist, he must be open to both possibilities. While the origin of our universe is still a mystery, there was a contentious argument about how the universe would end. The fate of the cosmos hinges on what types of matter and energy populate it, and these ingredients ultimately shape how it evolves over time. Currently, two main possibilities are considered by cosmologists, and both of these scenarios offer a glimpse into radically different outcomes. In the first scenario, the universe will continue expanding indefinitely. This ever-widening growth has profound implications. Although stars are abundant now, they each have a limited lifespan and will eventually burn out. In a far-off future, long after humanity and perhaps any other sentient beings have disappeared, stars will extinguish, leaving behind stellar remnants scattered across a dark, silent cosmos. Dead stars in the form of white dwarfs, neutron stars, and black holes will remain, along with faint embers of long-faded light. But even in this bleak universe, there's potential for drama depending on the cosmic ingredients involved. Three primary components are thought to dominate the universe's composition: dark matter, dark energy, and regular matter, which includes protons, electrons, and the particles that make up everything familiar to us. Of these, dark energy is the most mysterious and crucial force in determining the future trajectory of the cosmos. This elusive substance is somewhat like a cosmic anti-gravity, pushing things apart rather than pulling them together. If dark energy is indeed a constant force, with a density that doesn't dilute as space stretches, it could cause the expansion to accelerate endlessly. In one dramatic scenario, dark energy's negative pressure could grow so strong that it literally tears apart everything, down to the smallest particles. Known as the Big Rip, this theory suggests that galaxies, stars, planets, and even atoms could be pulled apart, disintegrating the very fabric of matter. In such a universe, the fate of everything would be reduced to its most basic components, hence, from particles to particles. The journey from dust to dust would instead become a return to a chaotic ocean of particles. Alternatively, it's possible that dark energy may not be as stable as we think. Its power might decrease over time, and with this change, the cosmic acceleration would gradually slow down. In this case, the expansion would continue, but at a calmer, less extreme pace. The universe would still end up as a collection of burnt-out stars and blackened stellar remnants scattered across vast distances, but without the brutal tearing apart that the Big Rip scenario proposes. This type of ending, often called the cold death or heat death, is marked by eternal isolation. Objects are spread so thinly that they can no longer interact in any meaningful way, leaving a universe in stasis. This quiet cosmic ending has its own sort of poignancy. Without any way for matter to coalesce or for energy to shift in meaningful ways, the universe would essentially be frozen in a state of ultimate entropy. In such a scenario, there would be no more surprises, no potential for new forms or structures, and no prospect for life. Time would effectively lose its meaning as nothing new could occur. In a way, time itself would end, with no future left to unfold, no present to experience change, and only a vast, silent expanse stretching out indefinitely. But there's another intriguing possibility. The universe could, at some point, stop expanding and begin contracting. For this to happen, there would need to be enough matter to counteract the push of dark energy and eventually bring the expansion to a halt. Should this be the case, gravitational forces could pull everything back inward, reversing the spread and initiating a period of contraction. The dispersed matter would start to gather, and over billions of years, the universe would collapse back into a small, dense state. This shrinking could lead to what scientists call the Big Crunch, a theoretical mirror to the Big Bang. In a Big Crunch scenario, all matter and energy would condense into an incredibly hot and dense point, potentially obliterating everything as it compresses. However, some theorists propose that this ultimate compression might not be the end. Instead of reaching a singularity or a point of infinite density, the universe might rebound, expanding once again in what is known as a bounce model. In this version of cosmic events, the universe would cycle through endless phases of expansion and contraction, a rhythm of existence and collapse. Each cycle would see the end of time as we know it, but every ending would simultaneously mark the start of a new cosmic chapter. The possibility of an ever-recycling universe, oscillating between creation and destruction, offers a kind of hope, albeit with a fiery twist. Unlike the quiet and lonely death of the cold universe, the bounce model promises a dynamic, if harsh, renewal. Time, in this scenario, would be infinite, though constantly reset with each cycle. There would always be another beginning, another chance for existence to emerge anew. This concept, in a way, feels more comforting, suggesting that the universe is not a one-way journey to oblivion, but a perpetual sequence of rebirth. Looking at these cosmic possibilities, we realize how remarkably fortunate we are to live in this era of cosmic history. It's not a matter of luck, but rather a necessity of the universe's current structure. Life and consciousness, capable of pondering these cosmic questions, are only possible in a universe where stars exist long enough to nurture planets and complex organisms. In the distant future, conditions may no longer allow for life as we know it. The elements and forces that enable our existence will shift, leaving the universe devoid of sentient beings capable of perceiving time or reflecting on its passage. The fact that we can contemplate these possibilities now emphasizes our unique place within the universe. Although we are small in the grand scale of things, we may be among the few, if not the only, forms of life to hold the universe's history within our minds. While we might never witness the universe's end, the ability to imagine its fate gives us a profound connection to the cosmos. We are, in essence, a fleeting but essential part of the universe's journey, bearing witness to a story that spans billions of years. Through our awareness, we give meaning to the vast, silent spaces of time and existence.
So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles.
For nearly 60 years, the Big Bang has reigned supreme as our most successful theory for explaining our cosmic origins. Beginning from a hot, dense, matter and radiation-rich state, the universe has expanded, cooled, and gravitated ever since. As it evolved, it formed protons and neutrons, the first light elements, stable atoms, and eventually stars, galaxies, planets, and complex chemistry capable of giving rise to life. Some 13.8 billion years after it all began, here we are, observing the still expanding universe and working to figure out exactly where it all came from and how it came to be the way it is today. However, the deeper we dig, the more the Big Bang picture breaks. How could the universe arise from nothing? That puzzle is why many scientists, including the famous physicist Brian Cox, strongly rejects the Big Bang theory. The problem gets more intense as the most powerful space telescope ever, the James Webb Space Telescope, obtained some very strong evidence demonstrating that the Big Bang wasn't truly the start of it all. That raises the question, what existed before the Big Bang? And if the Big Bang wasn't the beginning, well, what was? Stay tuned today as we shed some new light on the origin of the universe in today's episode of Eyes 200M. The first time the phrase the Big Bang was uttered was over 20 years after the idea was first described. Ironically, the term itself comes from one of theory's greatest detractors, Fred Hoyle, who was such a staunch advocate of the rival idea of a steady-state cosmology. In 1949, he appeared on BBC Radio and advocated for what he called the perfect cosmological principle, the notion that the universe was homogeneous in both space and time, meaning that any observer not only anywhere but any time would perceive the universe to be the same cosmic state. He went on to deride the opposing notion as a hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past, which he then called irrational and claimed to be outside science.
But I'm afraid I don't really believe in the Big Bang.
But the idea in its original form wasn't simply that all the universe's matter was created in one moment in the finite past. That notion, derided by Hoyle, had already evolved from its original meaning. Originally, the idea was that the universe itself, not just the matter within it, had emerged from a state of non-being in the finite past. And that idea, as wild as it sounds, was an inevitable but difficult to accept consequence of the new theory of gravity put forth by Einstein way back in 1915, his theory of general relativity. When Einstein first cooked up the general theory of relativity, our concept of gravity forever shifted from the prevailing notion of Newtonian gravity. Under Newton's laws, the way that gravitation worked was that any and all masses in the universe exerted a force on one another, instantaneously across space, in direct proportion to the product of their masses, and inversely proportional to the square of the distance between them. But in the aftermath of his discovery of special relativity, Einstein and many others quickly recognized that there was no such thing as a universally applicable definition of what distance was, or even what instantaneously meant, with respect to two different locations. With the introduction of Einstein's relativity, the notion that observers in different frames of reference would all have their own unique, equally valid perspectives on what distances between objects were and how the passage of time worked, it was only almost immediate that the previous absolute concepts of space and time were woven together into a single fabric, space-time. All objects in the universe moved through this fabric, and the task for a novel theory of gravitivity would be to explain how not just masses, but all forms of energy shaped this fabric that underpinned the universe itself. Although the laws that governed how gravitation worked in our universe were put forth in 1915, the critical information about how our universe was structured had not yet come in. While some astronomers favored the notion that many objects in the sky were actually island universes that were located well outside the Milky Way galaxy, most astronomers at the time thought that the Milky Way galaxy represented the full extent of the universe. Einstein sided with this latter view and, thinking the universe was static and eternal, added a special type of fudge factor into his equations, a cosmological constant. Although it was mathematically permissible to make this addition, the reason Einstein did so was because, without one, the laws of general relativity would ensure that a universe that was evenly, uniformly distributed with matter, which ours seemed to be, would be unstable against gravitational collapse. In fact, it was very easy to demonstrate that any initially uniform distribution of motionless matter, regardless of shape or size, would inevitably collapse into a singular state under its own gravitational pull. By introducing this extra term of cosmological constant, Einstein could tune it so that it would balance out the inward pull of gravity by proverbially pushing the universe out with an equal and opposing action. But the two developments, one theoretical and one observational, would quickly change this early story that Einstein and others had told themselves. In 1922, Alexander Friedmann worked out fully the equations that governed a universe that was isotropically the same in all directions and homogeneously the same in all directions, filled with any type of matter, radiation, or other forms of energy. He found that such a universe would never remain static, not even in the presence of a cosmological constant, and that it must either expand or contract, depending on the specifics of its initial conditions. In 1923, Edwin Hubble became the first to determine that the spiral nebulae in our skies were not contained within the Milky Way galaxy, but rather were located many times farther away than that of any objects that comprised our home galaxy. The spirals and ellipticals found throughout the universe were, in fact, their own island universes, now known as galaxies, and that, moreover, as had been previously observed by Vesto Slipher, the vast majority of them appearing to be moving away from us at remarkable speeds. In 1927, Georges Lemaitre became the first person to put these pieces of information together, recognizing that the universe today is expanding, and that if things are getting farther apart and less dense today, then they must have been closer together and denser in the past. Extrapolating this back all the way to its logical conclusion, he deducted that the universe must have expanded to its present state from a single point of origin, which he called either the cosmic egg or the primeval atom. This was the original notion of what would grow into the modern-day theory of the Big Bang. The idea that the universe had a beginning, or a day without yesterday. It was not, however, generally accepted for some time. Lemaitre originally sent his ideas to Einstein, who infamously dismissed Lemaitre's work by responding, "Your calculations are correct, but your physics is abominable." Despite the resistance to his ideas, however, Lemaitre would be vindicated by further observations of the universe. Many more galaxies would have their distances and redshifts measured, leading to the overwhelming conclusion that the universe was, and still is, expanding, equally and uniformly in all directions, on large cosmic scales. In the 1930s, Einstein conceded, referring to his introduction of the cosmological constant in an attempt to keep the universe static as his greatest blunder. However, the next great development in the formulating of what we know as the Big Bang wouldn't come until the 1940s, when George Gamow, perhaps not so coincidentally, an advisee of Alexander Friedman, came along. In a remarkable leap forward, he recognized that the universe was not only full of matter, but also radiation, and that radiation evolved somewhat differently from matter in an expanding universe. Gamow leveraged this fact to make three great generic predictions about the young universe. Number one, at some point the universe's radiation was hot enough so that every neutral atom would have been ionized by a quantum of radiation, and that this leftover bath of radiation should still persist today at only a few degrees above absolute zero. Number two, at some even earlier point, it would have been too hot to even form stable atomic nuclei, and so an earlier stage of nuclear fusion should have occurred, where an initial mix of protons and neutrons should have fused together to create an initial set of atomic nuclei, an abundance of elements that predates the formation of atoms. And number three, finally, this means that there would be some point in the universe's history, after atoms had formed, where gravitation pulled this matter together into clumps, leading to the formation of stars and galaxies for the first time. These three major points, along with the already observed expansion of the universe, form what we know today as the four cornerstones of the Big Bang. Although one was still free to extrapolate the universe back to an arbitrarily small, dense state, even to a singularity, if you're daring enough to do so, that was no longer the part of the Big Bang theory that had any predictive power to it. Instead, it was the emergence of the universe from a hot, dense state that led to our concrete predictions about the universe. Over the 1960s and 1970s, as well as ever since, a combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. Point: the discovery of the cosmic microwave background and the subsequent measurement of its temperature and the black body nature of its spectrum eliminated alternate theories such as the steady-state model. Point: The measured abundances of the light elements throughout the universe verified the predictions of Big Bang nucleosynthesis, while also demonstrating the need for fusion in stars to provide the heavy elements in our cosmos. Point. And the farther away we look in space, the less grown up and evolved galaxies and stellar populations appear to be, while the largest scale structures like galaxy groups and clusters are less rich and abundant the farther back we look. The Big Bang, as verified by our observations, accurately and precisely describes the emergence of our universe, as we see it, from a hot, dense, almost perfectly uniform early stage. But what about the beginning of time? What about the original idea of a singularity and an arbitrarily hot, dense state from which space and time themselves could have first emerged? That's a different conversation today than it was back in the 1970s and earlier. Back then, we knew that we could extrapolate the hot Big Bang back in time, back to the first fraction of a second of the observable universe's history. Between what we could learn from particle colliders and what we could observe in the deepest depths of space, we had lots of evidence that this picture accurately described our universe. But at the absolute earliest times, this picture breaks down. There was a new idea proposed and developed in the 1980s, known as the cosmological inflation, that made a slew of predictions that contrasted with those that arose from the idea of a singularity at the start of the hot Big Bang. In particular, inflation predicted the following points. Point: a curvature for the universe that was indistinguishable from flat, to the level of between 99.99% and 99.9999%. Comparably, a singularly hot universe made no prediction at all. Point: equal temperatures and properties for the universe, even in causally disconnected regions. A universe with a singular beginning made no such prediction. Point: a universe devoid of exotic high-energy relics like magnetic monopoles. An arbitrarily hot universe would possess them. Point: a universe seeded with small magnitude fluctuations that were almost, but not perfectly, scale invariant. A non-inflationary universe produces large magnitude fluctuations that conflict with such observations. Point: a universe where 100% of the fluctuations are adiabatic and 0% are isocurvature. A non-inflationary universe has no preference. Point: a universe with fluctuations on scales larger than the cosmic horizon, a universe originating solely from a hot Big Bang, cannot have them. And finally, point: and a universe that reached a finite maximum temperature that's well below the Planck scale, as opposed to one whose maximum temperature reached all the way up to that energy scale. The first 3 points were postdictions of inflation. The latter 4 were predictions that had not yet been observed when they were made. On all of these accounts, the inflationary picture has succeeded in ways that the hot Big Bang, without inflation, has not. During inflation, the universe must have been devoid of matter and radiation, and instead containing some sort of energy, whether inherent to space or as part of a field, that didn't dilute as the universe expanded. This means that inflationary expansion, unlike matter and radiation, didn't follow a proper law that leads back to a singularity, but rather is exponential in character. One of the fascinating aspects about this is that something that increases exponentially, even if you extrapolate it back to arbitrarily early times, even to a time where t is greater than -0, it never reaches a singular beginning. Now, there are many reasons to believe that the inflationary state wasn't one that was eternal to the past, that there might have been a pre-inflationary state that gave rise to inflation, and that, whatever that pre-inflationary state was, perhaps it did have a beginning. There are some theorems that have been proven and loopholes discovered to those theorems, some of which have been closed and some of which remain open, and this remains an active and an exciting area of research still today. But one thing is for certain: whether there was a singular, ultimate beginning to all of existence or not, it no longer has anything to do with the hot Big Bang that describes our universe from that moment that inflation ended, the hot Big Bang occurred, the universe became filled with matter and radiation and more, and it began expanding, cooling, and gravitating, eventually leading to our present day. There are still a minority of astronomers, astrophysicists, and cosmologists who use the Big Bang to refer to this theorized beginning and emergence of time and space. But not only is that not a foregone conclusion anymore, but it doesn't have anything to do with the hot Big Bang that gave rise to our universe. The original definition of the Big Bang has now changed, just as our understanding of the universe has changed. If you're still behind, well, that's okay. The best time to catch up is always right now. Indeed, because more and more evidence is showing that the Big Bang wasn't really the beginning of it all. Typically, earlier this year, NASA's time machine, the James Webb Space Telescope, finds evidence of massive galaxies that defy theories of the early universe. These galaxies, described in a new study based on Webb's first data released, are so far away that they appear only as a tiny reddish dot to the powerful telescope. By analyzing the light emitted by these galaxies, astronomers established that they were viewing them in our universe's infancy only 500 to 700 million years after the Big Bang. Such early galaxies are not in themselves surprising. Astronomers expected that first star clusters sprung up shortly after the universe moved out of the so-called Dark Ages, the first 400 million years or so of its existence, when only a thick fog of hydrogen atoms permeated space. But the galaxies found in the Webb images appeared shockingly big, and the stars in them too old. The new findings are in conflict with existing ideas of how the universe looked and evolved in its early years, and don't match early observations made by Webb's less powerful predecessor, the Hubble Space Telescope. We had specific expectations for the type of galaxies that live in the early universe. They are young and small, Joel Leja, assistant professor of astronomy and astrophysics at Penn State University and one of the authors of the study, told Space.com in an email. Previous studies of the early universe with Hubble and other instruments tend to find small, blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. Young stars, in general, shine bright blue. With age, stars develop a redder glow as they burn through their fuel and cool down. In ancient galaxies that Webb was built to spot, astronomers had not expected to see old red stars. They also had not expected to find galaxies more massive than perhaps 1 billion suns. But those reddish dots, revealed in Webb's deep fields, appear 50 times more massive than that. This was astounding. We're finding galaxy candidates as massive as our own galaxy when the universe was 3% its current age, Leja said. Leja also said that before astronomers start rewriting cosmology theories to explain how these galaxies came together so quickly after the Big Bang, they will have to ensure the odd red dots they are looking at are not something else. However, most of the alternative explanations also require entirely new concepts. For example, he said, stars in the early universe might emit light in exotic ways due to their lack of heavy elements, and perhaps we're not incorporating those in our models. Or, alternatively, perhaps our understanding of how stars form locally, example, how many stars form from gas as a function of the mass of the stars, is totally inapplicable in the early universe. These things would also be exciting to discover and would also overturn our understanding of star formation in the early universe, just in a very different way." End quote. The images that revealed these puzzling galaxies were obtained by Webb's Near-Infrared Camera, or NIRCam, as part of the Cosmic Evolution Early Release Science, or CEERS program. Astronomers plan to soon turn Webb's mirror to these galaxies again to, this time, obtain light spectra from those distant dots. Spectra break down the observed light according to its wavelength composition, and thus reveal the chemical and physical properties of its source. The most important thing is that spectra gives very precise distances to these objects, said Leja. The distance and the identity of these objects is correlated. If we know the distance, we can pin down the identity and vice versa. So, a spectrum will pretty immediately tell us if our hypotheses are correct or not. Only a little more than 6 months after the Webb team released the first observations from the Grand Observatory, scientists are already challenged to rewrite their theories about the early universe. This is very exciting. As Leja said in a Penn University statement, "We looked into the very early universe for the first time and had no idea what we are going to find. It turns out we found something so unexpected it actually creates problems for science. It calls the whole picture of early galaxy formation into question." End quote. Well, that's all we have for you today. We hope you enjoyed today's episode. Thanks for watching. We'll see you next time.
You know, we say the universe began 13.8 billion years ago. So that's a measurement. So because we can measure the speed that all the galaxies are flying away from us, essentially. And then you can run time backwards, if you like, so to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal.
One of the greatest scientific successes over the past century was the theory of the hot Big Bang. The idea that the universe, as we observe it, and exist within it today, emerged from a hotter, denser, more uniform past. Originally proposed as a serious alternative to some of the more mainstream explanations for the expanding universe, it was shockingly confirmed in the mid-1960s with the discovery of the primeval fireball that remained from the early hot and dense state, today known as the cosmic microwave background. For more than 50 years, the Big Bang has reigned supreme as the theory describing our cosmic origins, with an early inflationary period preceding it and setting it all up. Regardless, both cosmic inflation and the Big Bang have been continually challenged by astronomers and astrophysicists. And the latest to differ is 2020 Nobel laureate Roger Penrose. According to Roger Penrose, the Big Bang was not the start of our universe, rather, it was the end of the previous one.
Well, first of all, it is a Big Bang model. In other words, there is a Big Bang, but the Big Bang was not the beginning.
But does this hold true? Was there a universe before the Big Bang? And the Big Bang theory, is it wrong? Join us today as we dig deep into the new shocking theory that could defy our understanding of the beginning of the universe. When astronomers think about how the universe has evolved, they divide the past into distinct eras. They start with the Big Bang. Each subsequent era spans a different length of time. Important events characterize each period and lead directly into the next era. No one truly knows how to describe the Big Bang. We can sort of imagine it as a gigantic explosion. But a typical explosion expands into space. The Big Bang, however, was an explosion of space. Space didn't exist until the Big Bang. In fact, the Big Bang was not only the beginning of space, it was also the beginning of energy and matter. Ever since that cataclysmic beginning, the universe has been cooling. Hotter things have more energy. And physicists know that things with very high energy can flip back and forth between existing as matter or as energy. So, you can think of this timeline as describing how the universe gradually changed from being pure energy to existing as different mixes of matter and energy. And all of it began with the Big Bang. 0 to 10 to the 43rd second, or 0.00000, well, you get the point, 42 zeros, 01 seconds after the Big Bang. This period is known as the Planck era. It goes from that instant of the Big Bang to this minuscule fraction of a second afterwards. Current physics, our understanding of the basic laws of energy and matter, cannot describe what happened here. Scientists are theorizing how to explain what happened during this time, and in order to do so, they will have to find a law of physics to unify gravity, relativity, and quantum mechanics, the behavior of matter on the scale of atoms or subatomic particles. This extremely brief period serves as an important milestone because it is only after this moment that we can explain the evolution of our universe. 10 to negative 43 to 10 to negative 35 second after the Big Bang. Even within this tiny span of time, known as the Grand Unified Theory, or the acronym GUT era, major changes take place. The most important event during this time, gravity becomes its own distinct force and separates from everything else. 10 to minus 35 to 10 to minus 32 second after the Big Bang. During this short snippet of time, known as the era of inflation, the strong nuclear force separates from the remaining two unified forces, the electromagnetic and weak. Scientists are still not sure how and why this happened, but they believe it sparked an intense expansion or inflation of the universe. Measurements of the expansion during this time are extremely hard to comprehend. It seems that the universe grew by some 100 million billion times. That's a 1 followed by 26 zeros, by the way. Things at this point are really strange. Energy exists, but light as we know it does not. That's because light is a wave that travels through space, and there is no open space yet. In fact, space is so crammed full of high-energy phenomena right now that matter itself cannot yet exist. Sometimes astronomers refer to the universe during this time as soup, because it's just so hard to imagine how thick and energetic it would have been. But even the name soup is a poor descriptor. The cosmos at this time is thick with energy, not matter. The most important thing to understand about the inflation era is that anything that was just a little bit different before inflation will become something that is a lot different later. Hold on to that thought. It will be important shortly. 10 to minus 32 to 10 to minus 10 seconds after the Big Bang is the electroweak era. The weak force separates into its own unique interaction so that all four fundamental forces are now in place: gravity, the strong nuclear, weak nuclear, and electromagnetic forces. The fact that these four forces are now independent lays the foundation for everything we know now about physics. The universe is still too hot, too full of energy that is, for any physical matter to exist. But bosons, the subatomic W, Z, and Higgs particles, have emerged as carriers for the fundamental forces. 10 to minus 10 to 10 to minus 3, or 0.001 seconds after the Big Bang. This fraction of the first second is known as the particle era, and it's full of exciting changes. You probably have a photograph of yourself as a small child in which you start to see features that truly look like you. Maybe it's a freckle that formed on your cheek or the shape of your face. For the cosmos, this transitional time from the electroweak era to the particle era is like that. When it's over, some of the basic building blocks of atoms will finally have been formed. For instance, quarks will have become stable enough to combine to form elementary particles. However, matter and antimatter are equally abundant. This means that as soon as a particle forms, it almost immediately gets annihilated by its antimatter opposite. Nothing lasts for more than an instant in this era, but by the end of this particle era, the universe had cooled enough to enable the next phase to start, one that moves us towards normal matter. 10 to minus 3, or 0.001 seconds, to 3 minutes after the Big Bang. At last we've reached a time, the era of nucleosynthesis, that we can really begin to wrap our heads around. For reasons no one fully yet understands, antimatter has now become exceedingly rare. As a result, annihilations of matter and antimatter no longer happen as often. This allows our universe to grow almost entirely from that leftover matter. Space continues to stretch, too. The energy from the Big Bang keeps cooling off, and that lets heavier particles, like protons and neutrons and electrons, begin to form. There's still lots of energy all around, but the stuff of the cosmos has stabilized, so that it is now almost entirely made of matter. Protons, neutrons, electrons, and neutrinos have become abundant and are beginning to interact. Some protons and neutrons fuse into the first atomic nuclei. Still, only the very simplest ones can form: hydrogen, 1 proton plus 1 neutron, and helium, 2 protons plus 2 neutrons. By the end of the first 3 minutes, the universe has cooled so much that this primordial nuclear fusion comes to an end. It is still too hot to form balanced atoms, meaning with positive nuclei and negative electrons, but these nuclei seal the makeup of our cosmos' future matter: 3 parts hydrogen to 1 part helium. The ratio is still much the same today. And about 380,000 years after the Big Bang, matter cooled enough for electrons to combine with nuclei to form neutral atoms. This phase is known as recombination, and the absorption of free electrons caused the universe to become transparent. The light that was unleashed at this time is detectable today in the form of radiation from the cosmic microwave background. Some nearly 60 years ago, this background of cosmic radiation was first detected, catapulting the Big Bang from one of a few viable options for our universe's origin to the only one consistent with the data. While most astronomers and astrophysicists immediately accepted the Big Bang theory itself faced stiff challenges from some who wanted to disprove it for years. And as we mentioned, the latest to differ is Roger Penrose. For those who don't know, Penrose is a British mathematician, mathematical physicist, philosopher of science, and Nobel laureate in physics. He has contributed to the mathematical physics of general relativity and cosmology. He has received several prizes and awards, including the 1988 Wolf Prize in Physics, which he shared with Stephen Hawking for the Penrose-Hawking singularity theorems, and of course the 2020 Nobel Prize in Physics, quote, for the discovery that black hole formation is a robust prediction of the general theory of relativity, end quote. He is regarded as one of the greatest living physicists and mathematicians and scientists of all time, and is particularly noted for the breadth and depth of his work in both natural and formal sciences. But in recent years, Nobel laureate Roger Penrose has spent a large amount of his efforts on a crusade to overthrow the Big Bang, the supreme theory describing our cosmic origin. According to Penrose, drawing from the only evidence left behind after the Big Bang, the cosmic microwave background radiation, which was thrust into existence when the universe was just 300,000 years old, the Big Bang wasn't the beginning, but instead, it was only one in a series of cyclical Big Bangs, or eons, each of which spawned a new chapter in the universe's history. In the simplest possible terms, Sir Roger Penrose, that's right, he was knighted, believes that our universe is not the first, nor will it be the last to spawn from a dense mass of highly ordered everything into the complex universe we see all around us. The current Big Bang model, which is particularly grounded in inflation, doesn't supply a reason as to why a low entropy, high-ordered state existed at the birth of our universe. That is, unless things were set in motion long before the Big Bang actually occurred. In Penrose's theory, our universe has, and will again, return to a state of low entropy as it approaches its final days of expanding into eventual nothingness, leaving behind a cold, dark, featureless abyss. By virtue, black holes, the vacuum cleaners of our universe, which leak radiation and destroy everything they touch, spend their cosmic lifetimes working to scrub entropy from the universe. As the universe nears the end of its expansion, the remainder of its black holes will evaporate or gobble up one another, thus setting things back into a state of order. During this period, the universe would begin to revert back into a similar state it was in the beginning of the Big Bang, when the geometry of space-time will become smooth again, which is in stark contrast to its current jagged form. According to Penrose's model, this will usher in the new eon, after the universe is no longer able to expand any further. So, it collapses back in on itself as a highly ordered system, one that is ready to trigger the next Big Bang. The current model of the universe says that any temperature variations in the CMB should be random or Gaussian, but Penrose claims that he and his partner V. Gurzadin, who hails from the Yerevan Physics Institute in Armenia, have found more than 12 very clear concentric circles within the data, which was collected by NASA's WMAP satellite program over the course of a 7-year period, where there are regions when the radiation have a much smaller temperature range. To him, these posits are spherical evidence of the gravitational waves, massive ripples in space-time that are created through the collision of massive black holes, which took place during the previous eon. Of course, if his hypothesis, which has been dubbed conformal cyclic cosmology, were validated, it would suggest that the current state of our universe is merely one of perhaps an infinite number of eons, which also means that there is no need for a precursor for the Big Bang. I claim that this eon is one of a succession of such things, where the remote future of the previous eons somehow becomes the Big Bang of our eon, Penrose said. Of course, his conclusion has been criticized among physicists, but it's still an interesting hypothesis, with vast implications, if true. And in fact, the idea of cyclic universes is not a completely new idea. In the past, many scientists predicted that the universe would end in a big crunch, a hypothetical scenario for the ultimate fate of the universe, in which the expansion of the universe eventually reverses and the universe recollapses, ultimately causing the cosmic scale factor to reach zero, an event potentially followed by a reformation of the universe starting with another Big Bang. The vast majority of evidence indicates that this hypothesis, though, is not correct. Instead, astronomical observations show that the expansion of the universe is accelerating rather than being slowed by gravity, suggesting that the universe is far more likely to end in heat death. The theory dates back to 1922, when Russian physicist Alexander Friedmann, creating a set of equations, showed that the end of the universe depends on its density. It could either expand or contract rather than stay stable. With enough matter, gravity could stop the universe's expansion and eventually reverse it. This reversal would result in the universe collapsing on itself, not too dissimilar to a black hole. The outcome of the universe can be seen by seeing which force will beat out the other one. One is the explosive force from the Big Bang, and the other is gravity. If gravity overcomes the force of the Big Bang, then the Big Crunch will start, reversing the Big Bang. However, if this doesn't happen, heat death is the most likely scenario. While astronomers know that the universe is expanding, there is no consensus or data on how large the force of expansion actually is. The ending of the Big Crunch would get filled with radiation from stars and high-energy particles, When this is condensed and blue shifted to higher energy, it would be intense enough to ignite the surface of stars before they collide. In the final moments, the universe would be one large fireball with a temperature of infinity, and at the absolute end, neither time nor space would remain. The Big Crunch theory also leads into another theory known as the Big Bounce, in which after the Big Crunch destroys the universe, it does a sort of bounce, causing another Big Bang. This could potentially repeat forever in a phenomenon known as a cyclic universe. But most scientists believe that the universe might yet collapse into a Big Crunch. And that is because the appearance of dark energy. When we first uncovered the presence of dark energy, we weren't able to measure its properties well at all. We could tell it wasn't matter or radiation, as we could tell that it had some sort of pressure that was negative overall. However, as we gathered better data, particularly from type 1a supernova, from the imperfections in the cosmic microwave background, and from measuring how the universe's large-scale structure evolved over cosmic time, our constraints began to improve. By the year 2000, it was clear that dark energy's pressure was more negative than cosmic strings or spatial curvature could account for. By the mid-2000s, it was clear that dark energy was most consistent with a cosmological constant, but with an uncertainty that was still pretty large, of about plus or minus 30 to 50%. However, measurements of the cosmic microwave background's polarization from WMAP improved measurements by Planck, and measuring how galaxies are correlated throughout space and time through surveys like the 2-degree field Wiggle-Z and the Sloan Digital Sky Survey gradually reduced those errors. By the early 2010s, dark energy still looked like a cosmological constant, but the uncertainties were down to plus or minus 12%. And by the late 2010s, they were down to plus or minus 8%. Today, they sit at around plus or minus 7%, with NASA's upcoming Nancy Roman telescope poised to reduce that uncertainty down to just plus or minus 1%. Both theoretically and observationally, we have every indication that dark energy is a cosmological constant. We know its pressure is equal to minus 1 multiplied by its energy density, and not negative 2/3 or negative 1 1/3. In fact, the only wiggle room we have is that there is some tiny variation across either space or time that lies below the limits of what we've been able to detect. Both theoretically and observationally, there's no reason to believe that such a variation exists. But that will never stop theorists from doing what they do best, playing in the proverbial sandbox of theorizing. Whenever you have an observational or experimental result that doesn't align with your expectations, what we typically do is modify the standard theory, or by adding something new in, a new particle, a new species, or a modification to the behavior of a known to exist species. Each new ingredient can have one or more free parameters to it, enabling us to tweak it to fit the data and to extract new predictions from it. In general, a good idea will explain many different discrepancies with few free parameters, and a bad idea will explain only one or two discrepancies with one or two parameters. Where do dark energy models that lead to a big crunch fall according to this criteria? Well, they add one or more new free parameters without explaining a single unexpected result. It doesn't even fall along the good idea, bad idea spectrum. It's simply unmotivated speculation, or as we call it in professional circles, complete garbage. It doesn't mean, ultimately, that dark energy won't undergo some sort of unexpected transition, and that its properties won't change in the future. It doesn't mean that it's impossible for such a transition to change the contents of the universe, even causing it to reverse course. And it doesn't mean that a big crunch is an impossible fate for us. If dark energy changes in ways we don't anticipate, it could indeed happen. But we shouldn't confuse "it isn't ruled out" with "there's any evidence at all indicating this ought to be the case." People have been modifying dark energy for over 20 years now, playing in the sandbox to their heart's content. In all that time, up to and including the present, not a single shred of evidence for dark energy's unexpected evolution has ever appeared. While some may argue that their explanations are beautiful, elegant, or attractive in some way, it's worth remember the aphorism known as Hitchin's razor. What can be asserted without evidence can be dismissed without evidence. According to all the evidence, dark energy is here to stay, and a big crunch, while possible, just doesn't describe the future fate of the universe we happen to live in just yet. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. And as always, thanks for watching, and we'll see you next time.
Brian Cox just announced the true scale of the universe. Our universe is continually expanding, making it challenging to determine its boundaries and dimensions. Thanks to the James Webb Space Telescope, humans can now peer into the farthest corners of the universe. As the James Webb Telescope embarks on its exploration journey, many scientists, such as Brian Cox, have revealed the actual scale and vastness of the universe. We know the cosmos is incredibly vast, but we have never seriously contemplated it. In the observable universe, scientists have estimated the existence of around 2 trillion galaxies. If you gaze at the night sky on a clear night, you might see about 6,000 stars. However, this number is just a tiny fraction of all the stars out there. The rest are too distant for us to perceive. So, how many stars are there in the sky? We know little about the universe, and in that ignorance, we find reason to expand our exploration. It's not just about discovering distant and marvelous objects. It's also an opportunity to understand ourselves. We are not mere observers. We are part of this grand event. Alan Watts was right when he said we are a way for the universe to know itself. Dive deep into the adventure of exploring our universe, where mysteries unfold before us, and simultaneously explore the infinite within ourselves. The universe beyond our reach. Humanity has always yearned for the boundless expanse beyond Earth. It is the realm of planets and stars, beyond the Milky Way, a vast cosmic abyss filled with galaxies yet to be counted, stretching billions of light years across the universe. To be precise, there are over 100 billion galaxies in our observable universe, meaning the universe as it exists relative to our current position is about 46.5 billion light years away. Our deepest observations, such as the Hubble Extreme Deep Field, XDF, have recently increased the count to nearly 200 billion galaxies as a lower limit, and there may still be many undiscovered galaxies waiting to be explored. But you might know that the Big Bang, or the birth of all the matter and energy in our universe, occurred just 13.7 billion years ago. And yet I just correctly told you that the observable universe goes as distant as 46.5 billion light years from us. The reason for this is that as light from distant galaxies travels to us, the space-time between them continues to expand, something it's been doing ever since the Big Bang. With our current understanding of what makes up the universe, including ordinary matter, radiation, dark matter, and dark energy, we know precisely how the expansion has unfolded up to this point and how it will continue in the future. Light has traveled to our eyes for 5 billion years, allowing us to see an object located about 6.1 billion light years away. And the light that just reached us after a real journey of 10 billion years is from an object now over 16 billion light years away. Since the expansion will persist in the future, all objects currently expanding away from us will do so at an increasingly faster rate, eventually disappearing from the part of the universe we can reach. The Virgo supercluster, the closest large galaxy cluster to us, is only 50 million light years away. If we were on a rocket moving at nearly the speed of light, we could approach any galaxy within it that we choose in less than 100 million years. You might think this is true for any galaxy, that if you can move arbitrarily close to the speed of light, you can reach any galaxy in the universe. This would be true if we lived in a universe without dark energy. But in our universe, you have your own limitations, and they only get worse over time. Due to the cosmic expansion, a galaxy that is farther away seems to be moving away from us faster, or its light is shifting towards the red. This image from a portion of the Hubble Ultra Deep Field shows galaxies with the highest redshifts ever observed. Moreover, you don't have to be extreme. Any galaxy with a redshift greater than 1.8, or about 16 billion light-years away now, is already beyond our reach. Even if we had a relatively relativistic spacecraft, even if we could move ourselves at the speed of light, we still couldn't reach it. Those galaxies will never receive our first broadcast, and in fact, from now on, nothing we do can affect them. They are gone. How many galaxies are there in the universe? The human mind is not capable of grasping the universe. We are like a little child entering a huge library. The walls are covered to the ceilings with books in many different tongues. The child knows that someone must have written those books. It does not know who or how. Or does not know who or how. It does not understand the languages in which they are written. But the child notes a definite plan in the arrangement of the books, a mysterious order which it does not comprehend, but only dimly suspect. Albert Einstein. Our Earth is a relatively large planet. Scientists estimate that Earth's maximum capacity could be up to 50 billion people. However, comparing our Earth to the Sun is like a visual representation of an ant seeing an elephant. The Sun is the largest star in the solar system. Its diameter can reach up to 1.4 million km, 100 times that of Earth, and its mass is 1.3 million times that of Earth. Of course, the volume of the Sun is 1.3 million times that of Earth. With this data, you can imagine how enormous the Sun is. Due to the gravitational force created by its massive weight, the Sun attracts other planets in the solar system, causing them to orbit around it. Ultimately, this gives rise to life on Earth with its day-night cycles and seasonal winds. The Sun may be large, but compared to the Milky Way, it is just one of many stars within countless solar systems existing in the universe. According to calculations by scientists, the diameter of the Milky Way can reach 100,000 to 160,000 light-years, and the Sun is just an ordinary and small star within the Milky Way. Many claim that there are numerous stars like the Sun in the Milky Way. However, our solar system is the only one in the Milky Way where life has been found. There are at least 100 billion stars like the Sun in the Milky Way, so the question arises, does the Milky Way truly have so many stars? The number of stars in a galaxy is closely related to its size. The Milky Way is a giant galaxy with a diameter of over 100,000 light-years in the universe. Although humans cannot know exactly how many stars are in the Milky Way, astronomical observations suggest that the number of stars in the Milky Way is indeed very large. Some scientists predict that there are 120 billion stars, while others suggest 200 billion, and some even speculate that the Milky Way contains over 300 billion stars. On every cloudless night, each star we see when gazing into the true space is a star within the Milky Way. Scientists also speculate that the Andromeda Galaxy, twice the size of the Milky Way, contains even more stars. It is estimated to have at least 600 to 700 billion stars, 2-3 times that of the Milky Way. Compared to the Milky Way, the size of Earth and even the Sun is incredibly minuscule because the Milky Way is truly enormous. Currently, with space technology, we can only travel within the range of Mars and cannot go beyond the solar system in the Milky Way. Therefore, the exact number of stars in the Milky Way or other galaxies is entirely incalculable and can only be estimated using techniques such as computer simulations. It is estimated primarily by the supermassive star clusters in the Milky Way. Humans use telescopes like the Hubble Space Telescope or radio telescopes to observe the Milky Way and capture various star clusters, such as NGC 362 and Omega Centauri. Each star cluster is a bright point on the Milky Way,
By calculating these bright points, scientists estimate the number of stars in the Milky Way. Each cluster contains hundreds of thousands of stars, and there are at least over 200 such clusters in the Milky Way, so there are hundreds of billions of stars in the Milky Way. The size of the universe always lies beyond human imagination. Galaxies contain hundreds of billions of stars. Who can imagine that there are hundreds of billions of galaxies like the Milky Way in the entire universe? Currently, humans still utilize the Hubble Space Telescope to explore the universe. Through continuous observations with the Hubble Space Telescope, the Hubble Deep Field has been discovered in the depth of space. The so-called Hubble Deep Field is a magnificent panorama of galaxies beyond our Milky Way that contains no stars. This region actually harbors at least 3,000 galaxies beyond our Milky Way, all originating from distant galaxies. For those curious about this term, the Hubble Deep Field, HDF, is an image of a small area in the constellation Ursa Major, constructed from a series of observations by the Hubble Space Telescope. It measures 2.5 arcminutes per side, covering 2/1,000,000 of the entire sky, equivalent to the angular size of a tennis ball at a distance of 100 meters. This image is composed of 342 individual exposures, taken with Hubble's planetary camera and wide-field and planetary camera, two over more than 10 consecutive days from December 18 to December 18 to December 28, 1995. The captured region is extremely small, so in the image only a few stars from the Milky Way in the nearby background are visible. Therefore, almost all 3,000 objects in the image are galaxies, some of which belong to the youngest and farthest known types. Because it contains a large number of very young galaxies, the Hubble Deep Field has become a significant image in studying the universe during a new epoch of formation, with related scientific papers cited over 800 times as of the end of 2008. Scientists estimate that the area of the Hubble Deep Field represents only 1/20th of the entire universe. It is speculated that there are at least hundreds of billions of galaxies as large as the Milky Way in the universe. With so many stars and galaxies in the universe, do you still believe that Earth is the only celestial body? If the probability of life is 1 in 100 billion, then given the vast number of celestial bodies in the universe, life could potentially arise thousands of times. Therefore, life on Earth seems not to be the only life in the universe, and we, humans, are like trapped in the Earth prison, meaning we know where we come from, but we don't know where the future will lead. This mystery can only be solved with breakthrough technologies in the future. How to estimate distances in space? The universe is so vast, and measuring such vast distances is challenging because conventional distance measuring devices are ineffective for celestial objects beyond the solar system. On Earth, radar can measure distances of hundreds of kilometers with ease. It can send out a wave at the speed of light and time how long it takes for the wave to hit an object and bounce back to the receiver. Then, it simply measures the time it takes for the wave to go out and come back, giving the distance to the object. However, for objects farther away, such as those beyond the solar system, radar is useless. According to Gallagher, an object closer to the universe is easier to measure its distance. For example, the sun or the moon. By projecting a beam of light onto their surfaces and measuring the time it takes for that beam of light to reflect back to Earth, the distance of the object can be inferred. However, for objects farther away in galaxies, this measurement becomes much more complex and time-consuming. Even if technology allows us to project an extremely powerful beam of light at an incredible speed and distance to those planets, it would still be challenging for anyone to wait thousands of years to see this reflected beam. For instance, take Proxima Centauri, a red dwarf star located approximately 4.2 light-years away from the solar system. Radar waves would take about 8.4 years to travel from Earth to Proxima Centauri and back. By the time the radar waves return, they would have lost all their energy, making it impossible to measure the distance. Therefore, for celestial bodies beyond the solar system, astronomers have to resort to the method of stellar parallax. In this case, Stellar parallax is a direct method of measuring the distance from Earth to celestial bodies near the solar system. If you raise a finger and look at it with each eye alternately, you'll notice it shifts against the background. The phenomenon of objects changing their positions relative to each other through different perspectives like this is called parallax. As the Earth orbits the Sun, the viewing angle from Earth to the stars changes. Stars closer to us will move more compared to the background stars, much farther away, while distant stars will move less. By measuring the angular shift of a star relative to the background stars, and knowing the Earth's displacement between the two snapshots of that star, astronomers can calculate the distance from Earth to that star, using the trigonometric principles we learned in high school. Stellar parallax allows astronomers to directly measure the distance from Earth to celestial bodies near the solar system. This method can be effective for objects that are a few hundred light years away from Earth. However, as the stars get farther, the margin of error increases, and the measured distance becomes less accurate for stars or celestial objects at extreme distances. Even though parallax loses accuracy at extremely distant distances, it remains the first step for astronomers to measure the distances to objects even farther away, using other distance estimation methods. Other methods for estimating distances to stars beyond the reach of parallax still build upon the foundation of stellar parallax. Another common example is astronomers relying on Cepheid variable stars. These stars flicker in a rhythmic, regular pattern, much like a heartbeat. The brightness of these stars is closely related to their heartbeat, while the pulsation reveals their true brightness, comparing that actual brightness to the brightness observed from Earth. Apparent brightness allows astronomers to determine how far away they are. However, for this technique to be accurate, astronomers first need to use the parallax method to measure the distances of nearby Cepheid stars. From there, they can calibrate the comparison table of the true brightness of Cepheid stars. Since Cepheids are exceptionally bright stars, they can be observed in galaxies millions of light years away from us. To estimate distances between Earth and even more distant galaxies, astronomers can rely on superluminous supernova explosions. These are incredibly powerful explosions. That occur when a massive star goes supernova, typically lasting from a few weeks to a few months. Similar to Cepheid stars, the brightening and fading of a superluminous supernova can reveal its true brightness. By comparing this with the brightness observed from Earth, we can deduce how far away it is. The Type Ia supernova SN1994D, bottom left, shine brighter than the galaxy containing it, NGC 4526. Image captured by the Hubble Space Telescope. Of course, this method also needs to be calibrated using the parallax method and the distance estimation methods for Cepheid stars. Without knowing the accurate distances to some supernova, there's no way to determine their true brightness, rendering this method ineffective. In reality, the entire observable matter makes up only 4s of the volume of the observable universe, and it will get worse over time. As the universe's clock ticks on, objects at the outer edge will continue to expand further away, receding from us faster. Though we can currently approach the Virgo cluster, in 100 billion years it will also disappear. In 100 billion years, I should clarify, this will be all that remains, all the islands in the cosmic ocean out there, all the galaxies beyond our own, if we think about the distant future, will ultimately find themselves alone in the universe, except for very few galaxies also part of their group, or cluster. Every galaxy we see, with very few exceptions, is just there for us to observe for a limited time, a blink of an eye in a universe that promises eternal existence in the future. However, today, everything is here. If we were to reach the Virgo cluster and instead be there, we would have about 1,000 galaxies there, including our entire observable universe, with our local group being part of the unseen cluster that had redshifted by that time. So, think about that the next time you gaze into the night sky. Today we embarked on a wondrous journey through the layers of the universe. From distant galaxies to yet-to-be-explored mysteries, we have glimpsed a small part of the beauty and power of the boundless cosmos. Yet this journey is not just about gazing into the far and marvelous, but also about looking within ourselves. We are a part of this vast universe, and through understanding it, we come to know ourselves better. Let's continue this adventure together, exploring the secrets of the universe and delving into the depths of our souls. Don't forget to like, subscribe, and share your thoughts in the comments. Let's make each journey more meaningful together. See you in the upcoming adventures on our channel. Thank you for being with us. Scientists have a really good picture of the very early universe, something we know and love as the Big Bang Theory. In this model, a long time ago, the universe was far smaller, far hotter, and far denser than it is today. In that early inferno 13.8 billion years ago, all the elements that make us what we are were formed in the span of about a dozen minutes. Even earlier, this thinking goes, at some point our entire universe, all the stars, all the galaxies, all the everything, was the size of a peach and had a temperature of over 1,000,000,000 degrees. Amazingly, this fantastical story holds up to all current observations. Astronomers have done everything from observing the leftover electromagnetic radiation from the young universe to measuring the abundance of the lightest elements and found that they all line up with what the Big Bang predicts. As far as we can tell, this is an accurate portrait of our early universe. But as good as it is, we know that the Big Bang picture is not complete. There's a puzzle piece missing, and that piece is the earliest moments of the universe itself. What came before the Big Bang? It's the question that always comes up when thinking about the origin of the universe. Most scientists simply ignore the question, as it seems to be too hard a nut to crack. But now, in a bold revelation, physicist and professor of particle physics, Brian Cox declared that he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head.
Well, we used to think that the universe emerged in that state, very hot and very dense at the beginning of time. And we used to call that the Big Bang. But now we strongly suspect that the universe existed before that. And in that sense, it's possible to speak of a time before the Big Bang.
Join us as we dig deep into how Brian Cox debunks the Big Bang with the creation story that came before the existence of the universe. The idea of the Big Bang first came about back in the 1920s and 1930s. When we looked out at distant galaxies, we discovered something peculiar. The farther away from us they were, the faster they appeared to be receding from us. According to the predictions of Einstein's general relativity, a static universe would be gravitationally unstable. Everything needed to either be moving away from one another or collapsing towards one another if the fabric of space obeyed his laws. The observation of this apparent recession taught us that the universe was expanding today. And if things are getting farther apart as time goes on, it means they were closer together in the distant past. An expanding universe doesn't just mean that things get farther apart as time goes on. It also means that the light existing in the universe stretches in wavelength as we travel forward in time. Since wavelength determines energy, shorter is more energetic. That means the universe cools as we age, and hence things were hotter in the past. Extrapolate this back far enough, and you'll come to a time where everything was so hot that not even neutral atoms could form. If this picture were correct, we should see a leftover glow of radiation today, in all directions, that had cooled to just a few degrees above absolute zero. The discovery of this cosmic microwave background in 1964 by Arno Penzias and Robert Wilson was a breathtaking confirmation of the Big Bang. It's tempting, therefore, to keep extrapolating backwards in time to when the universe was even hotter, denser, and more compact. If you continue to go back, you'll find a time where it was too hot to form atomic nuclei, where the radiation was so hot that any bound protons and neutrons would be blasted apart. a time where matter and antimatter pairs could spontaneously form, as the universe is so energetic that pairs of particles, antiparticles, can spontaneously be created. A time where individual protons and neutrons break down into a quark-gluon plasma, as the temperatures and densities are so high that the universe becomes denser than the inside of an atomic nucleus. And finally, a time where the density and temperature rise to infinite values, as all the matter and energy in the universe are contained within a single point, a singularity. This very final point, this singularity that represents where the laws of physics break down, also is understood to represent the origin of space and time. This was the ultimate idea of the Big Bang. Of course, everything except that last point has been confirmed to be true. We've created quark-gluon plasmas in the lab. We've created matter-antimatter pairs. We've done the calculations for which light elements should form and in what abundances during the early stages of the universe, made the measurements, and found that they match with the Big Bang's predictions. Coming forward even farther, we've measured the fluctuations in the cosmic microwave background and seen how gravitationally bound structures like stars and galaxies form and grow. Everywhere we look, we find a tremendous agreement between theory and observation. The Big Bang looks like a winner. Except, that is, in a few regards. 3 specific things you would expect from the Big Bang didn't happen. First, the universe doesn't have different temperatures in different directions, even though an area billions of light years away in one direction never had time, since the Big Bang, to interact with or exchange information with an area billions of light years in the opposite direction. Second, the universe doesn't have a measurable spatial curvature that's different from zero, even though a universe that's perfectly spatially flat requires a perfect balance between the initial expansion and the matter and radiation density. And last, the universe doesn't have any leftover ultra-high energy relics from the earliest times, even though the temperatures that would create these relics should have existed if the universe were arbitrarily hot. Theorists thinking about these problems started thinking of alternatives to a singularity to the Big Bang, and rather of what could recreate that hot, dense, expanding, cooling state while avoiding these problems. In December of 1979, Alan Guth hit upon a solution. Instead of an arbitrarily hot, dense state, the universe could have begun from a state where there was no matter, no radiation, no antimatter, no neutrinos, and no particles at all. All the energy present in the universe would rather be bound up in the fabric of space itself, a form of vacuum energy which causes the universe to expand at an exponential rate. In this cosmic state, quantum fluctuations would still exist, and so as space expanded, these fluctuations would get stretched across the universe, creating regions with slightly more or slightly less than average energy densities. And finally, when this phase of the universe, this period of inflation, came to an end, that energy would get converted into matter and radiation, creating the hot, dense state synonymous with the Big Bang. This was regarded as a compelling but speculative idea, but there was a way to test it. If we were able to measure the fluctuations in the Big Bang's leftover glow and they exhibited a particular pattern consistent with inflation's predictions, that would be a smoking gun for inflation. Furthermore, those fluctuations would have to be very small in magnitude, small enough that the universe could never have reached the temperatures necessary to create high-energy relics, and much smaller than the temperatures and densities where space and time would appear to emerge from a singularity. In the 1990s, 2000s, and then again in the 2010s, we measured those fluctuations in detail and found exactly that. The conclusion was inescapable. The hot Big Bang definitely happened, but it's not the beginning of the universe. At that time, there is a question that always comes up when thinking about the origin of the universe. What came before? What happened before the Big Bang? And if there was no before, What was the cause of the Big Bang in the first place? Until a few centuries ago, the answer was easy. Some eternal deity set everything in motion. Even Isaac Newton believed that God created the universe some 6,000 years ago. Later, many scientists, including young Albert Einstein, assumed the universe itself to be eternal and everlasting. But now, most scientists simply ignore the question, as it seems to be too hard a nut to crack. In fact, when astronomers talk about the Big Bang, they usually do not refer to the very beginning of the universe, but to the incredibly hot and compact state of the universe in the first couple of minutes of its existence. To some extent, this is because no one has a real clue about the true nature of time, let alone about the beginning of time. British physicist Julian Barber, for one, has argued that time doesn't even exist, except as an illusion in our minds. According to others, including Stephen Hawking, time came into existence together with the universe, rendering the whole concept of the word before meaningless. As such, asking what happened before the Big Bang would be like asking what lies north of the North Pole, or what distance is shorter than zero. Then again, we simply don't know whether or not there was time before the Big Bang. But Professor Brian Cox said that he has a bold idea. Never one to shy away from the big questions, Brian Cox expressed that he's ready to take on the story of the origin of our universe. The physicist investigated the crucial question of our existence, aiming to discover how the universe came to be. He discussed how discoveries of other galaxies have helped us comprehend how we came to be, as well as the technologies utilized along the route, as he looked at the different cutting-edge space missions that have gotten us closer to the answer. And in a world-shattering revelation, Brian Cox argued there was a time before the Big Bang, a time in which the universe did not exist at all. He explored this in his documentary series, Universe, where everything begins and ends, stating that before the launch point of the Big Bang, there was no matter at all. All that existed was space-time and an ocean of energy, almost still, but gently rippling. This place, as he said, should be imagined as a near-still ocean of energy filling the void. It would have had no structures, and the energy in the space would have caused it to stretch violently, something known in space as inflation. Flipping the Bible creation story on its head, Prof. Cox proceeded to explain the science creation story. And the crux of the story is an unimaginably violent expansion, which is known as inflation.
In the beginning, there was an ocean of energy that drove a rapid expansion of space, known as inflation.
There were ripples in the ocean. As inflation ended, the ocean of energy was converted into matter at the Big Bang, and the pattern of the ripples was imprinted into our universe as regions of slightly different density in the hydrogen and helium gas that formed shortly after the Big Bang.
The denser regions of gas collapsed to form the first stars and the first galaxies. And 9 billion years later, a new star formed in the Milky Way, the Sun. The star was joined by 8 planets, including Earth. And nearly 13.8 billion years after it all began, we emerged, blinking into the light. Notably, Brian Cox is not the only one to make such an argument about the beginning of the universe. A remarkable theoretical physics research has revealed a possible window into the very early universe, showing that it may be just the latest iteration of a bang-bounce cycle that has been going on for, well, at least once, and possibly forever. According to the study, the physics that we use to understand the early universe, a wonderfully complicated mishmash of general relativity and high-energy particle physics, can take us only so far before breaking down. As we try to push deeper and deeper into the first moments of our cosmos, the math gets harder and harder to solve, all the way to the point where it just quits. The main sign that we have terrain yet to be explored is the presence of a singularity, or a point of infinite density, at the beginning of the Big Bang. Taken at face value, this tells us that at one point, the universe was crammed into an infinitely tiny, infinitely dense point. This is obviously absurd, and what it really tells us is that We need new physics to solve this problem. Our current toolkit just isn't good enough. To save the day, we need some new physics, something that is capable of handling gravity and the other forces combined at ultra-high energies. And that's exactly what string theory claims to be, a model of physics that is capable of handling gravity and the other forces combined at ultra-high energies, which means that string theory claims it can explain the earliest moments of the universe. One of the earliest string theory notions is the ekpyrotic universe, which comes from the Greek word for conflagration, or fire. In this scenario, what we know as the Big Bang was sparked by something else happening before it. The Big Bang was not a beginning, but one part of a larger process. Extending the ekpyrotic concept has led to a theory, again motivated by string theory, called cyclic cosmology. Technically, the idea of the universe continually repeating itself is thousands of years old and predates physics, but string theory gave the idea firm mathematical grounding. The cyclic universe goes about exactly as you might imagine, continually bouncing between big bangs and big crunches, potentially for eternity back in time and for eternity into the future. As cool as this sounds, early versions of the cyclic model had difficulty matching observations, which is a major deal when you're trying to do science and not just telling stories around the campfire. The main hurdle was agreeing with our observations of the cosmic microwave background, the fossil light leftover from when the universe was only 380,000 years old. While we can't see directly past that wall of light, if you start theoretically tinkering with the physics of the infant cosmos, you affect that afterglow light pattern. And so, it seemed that a cyclic universe was a neat but incorrect idea. But the ekpyrotic torch has been kept lit over the years, and a paper published in March 2020 has explored the wrinkles in the mathematics and uncovered some previously missed opportunities. The two physicists who authored the study, Robert Brandenberger and Ziwei Wang, both of McGill University in Canada, found that in the moment of the bounce, when our universe shrinks to an incredibly small point and returns to a Big Bang state, it's possible to line everything up to get the proper observationally tested result. In other words, the complicated, and admittedly poorly understood, physics of this critical epoch may indeed allow for a radically revised view of our time and place in the cosmos. But to fully test this model, we'll have to wait for a new generation of cosmology experiments. So, let's wait to break out the ekpyrotic champagne. But note that it's just one of many hypotheses in which our universe is not unique, but part of a possibly infinite multiverse, one way or another. A wild new theory suggests there may be another anti-universe, running backward in time prior to the Big Bang. The idea assumes that the early universe was small, hot, and dense, and so uniform that time looks symmetric going backward and forward. If true, the new theory means that dark matter isn't so mysterious. It's just a new flavor of a ghostly particle called a neutrino that can only exist in this kind of universe. And the theory implies there would be no need for a period of inflation that rapidly expanded the size of the young cosmos soon after the Big Bang. If true, then future experiments to hunt for gravitational waves or to pin down the mass of neutrinos could answer once and for all whether this mirror anti-universe exists. Physicists have identified a set of fundamental symmetries in nature. The three most important symmetries are charge. If you flip the charges of all the particles involved in an interaction to their opposite charge, you'll get the same interaction. Parity. If you look at the mirror image of an interaction, you get the same result. And time. If you run an interaction backward in time, it looks the same. Physical interactions obey most of these symmetries most of the time, which means that there are sometimes violations. But physicists have never observed a violation of a combination of all three symmetries at the same time. If you take every single interaction observed in nature and flip the charges, take the mirror image and run it backward in time, those interactions behave exactly the same. This fundamental symmetry is given a name, CPT symmetry, in which C for charge, P for parity, and T for time. In a paper accepted for publication in the journal Annals of Physics, scientists propose extending this combined symmetry. Usually, this symmetry only applies to interactions, the forces and fields that make up the physics of the cosmos. But perhaps, if this is such an incredibly important symmetry, it applies to the whole entire universe itself. In other words, this idea extends this symmetry from applying to just the actors of the universe, forces and fields, to the stage itself, the entire physical object of the universe. We live in an expanding universe. This universe is filled with lots of particles doing lots of interesting things, and the evolution of the universe moves forward in time. If we extend the concept of CPT symmetry to our entire cosmos, then our view of the universe can't be the entire picture. Instead, there must be more. To preserve the CPT symmetry throughout the cosmos, there must be a mirror image cosmos that balances out our own. This cosmos would have all opposite charges than we have, be flipped in the mirror, and run backward in time. Our universe is just one of a twin. Taken together, the two universes obey CPT symmetry. The study researchers next asked what the consequences of such a universe would be. They found many wonderful things. For one, a CPT-respecting universe naturally expands and fills itself with particles, without the need for a long theorized period of rapid expansion known as inflation. While there's a lot of evidence that an event like inflation occurred, the theoretical picture of that event is incredibly fuzzy. It's so fuzzy that there is plenty of room for proposals of viable alternatives. Second, a CPT-respecting universe would add some additional neutrinos to the mix. There are 3 known neutrino flavors: the electron neutrino, muon neutrino, and tau neutrino. Strangely, all 3 of these neutrino flavors are left-handed, referring to the direction of its spin relative to its motion. All other particles known to physics have both left and right-handed varieties, so physicists have long wondered if there are additional right-handed neutrinos. A CPT-respecting universe would demand the existence of at least one right-handed neutrino species. This species would be largely invisible to physics experiments, only ever influencing the rest of the universe through gravity. But an invisible particle that floods the universe and only interacts via gravity sounds a lot like dark matter. The researchers found that the conditions imposed by obeying CPT symmetry would fill our universe with right-handed neutrinos, enough to account for the dark matter. But we would never have access to our twin, the CPT mirror universe, because it exists behind our Big Bang, before the beginning of our cosmos. But that doesn't mean we can't test this idea. The researchers found a few observational consequences of this idea. For one, they predict that the 3 known left-handed neutrino species should all be Majorana particles, which means that they are their own antiparticles, in contrast to normal particles like the electron, which have antimatter counterparts called the positrons. As of now, physicists aren't sure if neutrinos have this property or not. Additionally, they predict that one of the neutrino species should be massless. Currently, physicists can only place upper limits on the neutrino masses. If physicists can ever conclusively measure the neutrino masses, and one of them is indeed massless, that would greatly bolster the idea of a CPT symmetric universe. Lastly, in this model, the event of inflation never occurred. Instead, the universe filled with particles naturally on its own. Physicists believe that inflation shook space-time to such a tremendous degree that it flooded the cosmos with gravitational waves. Many experiments are on the hunt for these primordial gravitational waves, but in a CPT symmetric universe, no such waves should exist. So if those searches for primordial gravitational waves turn up empty, That might be a clue that this CPT mirror universe model is correct. In the end, we have to admit we're ignorant about the true beginning of the universe. And even if we lean towards an eternal multiverse with no real beginning at all, we don't know why there is something, or more to the point, why there is everything, instead of nothing. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.